This is part 2 of the review sheet for advanced functions probability test. So it says use this table to answer questions 8 and 9. Question 8 says, what is the probability that a randomly selected Californian is Hispanic? So let's look right here at California. Their total population is 33 million, and their Hispanic population is a little under 11 million, so 10.9 million. So if we want to know the probability of randomly selecting a Hispanic out of all the Californians, all we do is take the number of Hispanics, which would be 10,966,566, and then dividing that number by the total number of Californians, which is 33,871,648. So that means there's a point, the probability is 0.324 or 32.4%. So 0.324 would be the probability of selecting a Hispanic out of all the Californians. 9 says, what is the probability that a randomly selected person from Texas is not Hispanic? Okay, the simplest way to do this one is to actually find the probability that someone from Texas is Hispanic. Okay, and I'll show you why in a second. Because we can easily do that, because that would be the same process as number 8. We just divide the number of Hispanics in Texas by the number of total Texans, and we get 0.319. So if that's the probability that someone in Texas is Hispanic, then to find the probability that they are not Hispanic, you just do 1 minus that number. That gives us 0.680. So there's a 68% chance that someone we chose from Texas would not be Hispanic. Number 10, determine if the following event is independent or dependent. Remember, independent means they do not affect each other. Dependent means they do affect each other. Then find the probability. What is the probability of selecting a blue marble, not replacing it, then choosing a yellow marble from a box of 8 blues and 5 yellows? So we have 8 blues. 1, 2, 3, 4, 5, 6, 7, 8. And then I'll just have to use green for my yellows. I don't have a yellow marker. 5 yellows. Okay. So this is what's currently in the marble bag. So if I randomly pick right now, then the probability of getting a blue marble would be 8 out of 13. Because at the moment there are 8 blues and a total of 13 marbles. So now, though, I've taken a blue marble away. So I have changed the odds, because now there's only 12 total marbles, and there are 7 blues and 5 greens. So first of all, before I go any farther, this is a dependent problem, because by not replacing that marble, it changes the probability the next time around. So I'm choosing a yellow marble next. The probability of that would be 5 out of 12. So as you can see, this number has changed because we took a marble away. So when we go in and we pick that green marble out, there we go, when we pick that green marble out, we change the probability by picking that blue one first. So anytime you're trying to do two things at once, we're doing a blue and a yellow marble, then we are going to multiply them together. So 8 over 13 times 5 over 12. So 0.256. Number 11, determine the probability of selecting either a face card or a black card from a standard deck. Is this event mutually exclusive or mutually inclusive? Okay, events are exclusive if they cannot happen at the same time. They're inclusive if they can happen at the same time. They don't have to, but if it's possible for them to be happening simultaneously, they are inclusive. So if you think about a deck of cards, you have to say, is it possible to be a face card and a black card? Of course. So these can happen at the same time, which means they are mutually inclusive. And when that happens, we need to add their probabilities together and then subtract the probability of them happening at the same time. So I'll show you what I mean. We take the probability of having a face card, which as we did earlier is 12 out of 52. There's 4 queens, 4 kings, and 4 jacks for a total of 12 out of the 52. Add to that the probability of getting a black card. Well, half the cards are black, so that's 26 out of 52. But then we need to subtract the probability that it's both. The reason for that is we've counted those cards twice, so we need to take them away so we're not counting them twice. Because 6 of those face cards are black. Because remember, half are red, half are black. So half my face cards would be 6, and they're also black. So I need to add these together to get 32 over 52, and that gives me 8 over 13. Alright, now a person enters a raffle where 500 tickets are sold. If the winner of the raffle gets $300 and the runner-up gets $50, how much should each ticket be in order to make the game fair? So we start by talking about the different outcomes that are possible. The winner gets $300. So one person gets $300, one person gets $50, and everybody else gets 0. So when we do the probability, we're told that there are 500 tickets that are sold. So if one winner gets $300, then you have a 1 in 500 chance of getting $300. If one person wins $50, then you have a 1 out of 500 chance of getting $50. So that means there are 2 winning tickets in total, leaving 498 non-winners. So now we multiply 300 times 1 over 500, we get 0.6. 50 times 500, we get 0.1. And then 0 times 498, we're multiplying all of these, and we get 0. So to find the expected value of this game, we add these together. It gives us 0.7, or you can say 70 cents. So to make the game fair, someone would need to pay 70 cents for this game. Last problem. A box contains 21 bills, 10 fives, 2 20s, 1 50. It costs $5 to play. That allows you to randomly pick and keep 1 bill from the box. What is the expected value of playing this game? Okay, so this time we have 4 different outcomes. If we pay $5 and draw one of the $1, then we've lost $4. So I paid $5 for my opportunity and only picked a 1 out. So I lost $4. Or I could break even. If I paid $5 and drew a 5, then I just came out even. If I paid 5 and drew a 20, then that's a positive $15 that I made. And if I paid 5 and drew the 50, then I made $45 total. Now if we look, we see that there are 20, 10, 2, and 1, so that's a total of 33 total bills that we can draw from. So the probability of drawing the $1 is 20 out of 33. The probability of drawing one of the $5 is 10 out of 33. And then we have a 1 out of 33 chance, 2 out of 33 chance to draw the $20 bill, which will give us a $15 outcome, and a 1 out of 33 chance to get the $50 bill. So then we multiply all these together. Negative 4 times 20 over 33 gives us negative 2.42. We get 0 here, 0.90 repeating here, and 1.36 repeating here when we multiply all these together. Now if we add all these, it gives us our expected value. And for this particular game, expected value is negative 15 cents. So this game is not quite fair. We're overpaying by 15 cents. But the expected value is negative 15 cents. Good luck on the test, guys.